Good morning. We'll just wait for a couple of minutes. See that there are only 30 students there in the session. Okay, I think let me get started. I'm not sure whether the attendance will be better. Okay, I think the tutorial 2 marks have been released. I just want to inform you that the average class average was 14.23 out of 20. It's a good performance. Yeah, most of people have done well. I see that there are 2 students who got 20 marks, and there are about 5 students who got 19.5, another 5 students who got 19. Okay, uh, so the performance is good. I'm sure all of you will be happy about that. Okay, and what I'm little concerned is there are still about 10 students who have less than 30% marks, that is less than 6 marks. I think they need to do better, right? And I don't think it's such a tough subject to score such a low mark. Most of the questions asked in the tutorial are related to what has been discussed in class, right? If you have been following and if you have been practicing the problems, then it should not be difficult. Okay. So those students who got low marks, no, please concentrate and do a better preparation for the next 2 tutorials. Okay. There are a couple of clarifications about one question. I think that is the second question, 14-point multiplication. Right, I'll respond to that by email. Okay, by sometime today. Okay, it's a minor clarification only, so I'll respond to that. Okay, any other clarifications or queries about this tutorial 2? Again, as suggested, please look at the solutions and then see if there is any discrepancy with the solutions that you have there, right? Only if there is a discrepancy, please point it out explicitly when you submit the request for regrading. Okay. Yeah. So are there any other questions about this tutorial 2? So as announced, the tutorial 3 will be on next Thursday. It will include the sequential circuits and the generation of the machine code, which we have been discussing in the last couple of weeks. Okay. Then the tutorial 4 will be on the 12th of November. That will include the complete syllabus in the course. Okay, because it's like a makeup tutorial. If you want to improve your marks in the tutorials, or if you have missed any of the tutorials, right? So this will be the makeup tutorial. Okay. So finally, we'll take the best 3 out of these 4 tutorials for the grading. Okay. Yeah. Any other questions? And we received a large number of requests for the lab assignment regrading. That is assignments 1, 2, and 3. I'm going to discuss with the TS. It's not possible to reevaluate all the submissions because it takes enormous amount of time. Okay, we are going to look at only the regrade requests where the penalty was high. Okay, if the penalty is not very high. If it's less than 5 marks out of 40 or 50 marks totally, right, then we'll not process those regrade requests, because finally when these assignment marks are scaled to 10, right, it will be less than 1 mark. Okay, so let's not worry about that. So only if the penalty is higher than 5 marks, we'll consider those requests, right? So the TS will consider those regrade requests and then see if any revision is to be there in the marks. Okay, yeah, but that may take but another 1 week's time to process all the regrade requests. Yeah, any other questions? Okay, let's continue our discussion. See that still there are only about 45 students out of 90 students. I'm not sure whether I should really close the course now. If the half of the class is interested, right? If only half of the class is interested, right? Is it good to continue? Okay. Anyway, let's see how it goes. Okay. So in the last class, we were looking at what is called the execution of the machine code, and we looked at the simplest method called the sequential execution of the instructions, right? And typically, if every phase in the execution of the instructions, when I say the phase, we are talking about these 4 main phases: instruction fetch, instruction decode, and operand fetch. Then performing the operation in the ALU or in the memory, and then writing back the result in the register file. If we assume that each of these phases takes only 1 clock cycle, then every instruction takes 4 clock cycles. So the throughput will be 1 instruction in every 4 clock cycles, right? That will be rather low. So what we are looking at is how to improve this throughput. And if we target the throughput of 1 instruction per clock cycle, okay, then we have been looking at what is called the overlapped execution of instructions. That's followed in the what are called the pipelined process. So in the pipeline process, we go through the execution of the instructions in an overlapped manner. That is, we start with the instruction I1. In the first clock cycle, we perform the fetch. Then when it goes to the decode and the operand fetch in the clock cycle 2, then we get started with the instruction fetch for the next instruction, that is I2, right? And we continue like this. And you can see that at clock cycle 4 onwards, right, all the 4 phases or all the 4 stages in the pipeline processor are busy with 1 instruction or another. So the instruction fetch stage is processing the I4, the instruction decode stage is processing the I3, then perform operation stage is processing the I2, right? And the write back stage is processing I1. And this happens in every clock cycle after this clock cycle 4, right? And under certain assumptions, right, the execution of these n instructions in the given sequence will take n plus 3 clock cycles. So the throughput will be n plus 3 over n instructions per cycle. And typically n will be a few thousands or millions or even millions in a typical program, right? So the throughput can be considered to be 1 instruction per clock cycle. But this throughput is possible only under certain ideal conditions, is what we are looking at the end of the last class, right? So the assumptions that we made are that the operation in every stage, that is in any of these 4 stages, can be completed in 1 clock cycle for every instruction. And we'll be quickly seeing that we also make an assumption that there are no dependencies among the instructions. We'll understand what it means quickly. And also it's assumed that there are no jump instructions in the program here, or there are no function calls in the program here, right, which is not really true with any real program, right? And whenever these ideal conditions are not going to be satisfied, then the throughput will be less than 1 instruction per clock cycle, but it will be still close to 1 instruction per clock cycle. Maybe it will be 1.1 or 1.2 instructions per. It will be less than 1, so it will be 0.9 or 0.85. So that depends on the nature of the sequence of instructions that we are dealing with. So let's look at each of these assumptions that we are making and see how far it's a valid assumption. So let's look at this assumption called the operation in every stage can be completed in 1 clock cycle. So if you go back and look at what is being done in each of the stages, we see that in the instruction fetch, we try to fetch the instruction from the memory. And as I was mentioning, if the instruction that you are looking for is available in the cache memory, which is a fast memory, then we can typically complete the instruction fetch operation in 1 clock cycle, right? If it is not present in this instruction cache, if it is present in the later levels of cache or in the main memory, then it will take more number of clock cycles. And then we say that fetch instruction for that instruction will be what is called a multi-cycle operation, because it takes more than 1 clock cycle to complete this instruction fetch, right? Then this instruction is set to go through the instruction fetch stage for multiple cycles. So basically, it will be present in the instruction fetch stage for the multiple cycles until the instruction fetch is completed. Okay, and how many cycles it will take, it depends on whether that instruction is available in the first level of the cache, or it's available in the second level of cache, or typically there are 3 levels of cache in the current day systems, or it will not be there in any of the caches, and it may be there only in the main memory. And in that case, it may take several clock cycles, because the main memory is of the order of 20 nanoseconds access time, which means that it may be about 20 clock cycles. So in that case, the number of clock cycles to complete this instruction fetch operation will be tens of clock cycles, right? So our assumption will not be valid. So what happens for that instruction, the number of clock cycles taken to complete the execution will be larger than 1, right? And that will add to the total number of clock cycles required for the execution of the complete sequence of instructions. So your numerator term here, right, which is n plus 3, will not be valid anymore, right? It will be much more than that. Okay, so let's say on the average, there is an additional delta cycles that may be required to complete the instruction fetch, right? So the time taken only for the instruction fetch alone will be, on the average, it will be 1 plus delta if, right? If there are no multi-cycle operation for any of the instructions, then this delta if will be 0. Otherwise, it will be greater than 1. Okay, so this is one potential case for a multi-cycle operation. Now, if you look at the second stage here, where typically we perform the decoding of the instruction and then we fetch the register operands from the register file, all these operations can be completed in 1 clock cycle, because typically when you're talking about this RISC architecture, the instruction formats are simple, so the control unit can complete the instruction decode operation in less than 1 clock cycle, and it also can complete the operation of reading the operands from the registers. As we have seen, that's nothing but the delay of the demultiplexer, and the delay of the demultiplexer is not significant. So this can be completed in a 1 clock cycle, right? So typically this will be only a 1 cycle operation. So there will not be any additional delay in the instruction decode and the operand fetch stage for the RISC process. And when you come to the perform operation stage, we see that we may be performing either an arithmetic operation or logic operation in the ALU, or we will be performing the memory read or write operation in the data memory. Again, from whatever we have discussed, the time it takes for the ALU to complete the operation depends on the size of the operands and depends on the which arithmetic operation being carried out and which type of the data, right? So for some operations, this can be a multi-cycle operation. So typically for the integer addition subtraction operation for maybe up to 16 bits or 32 bits, you may complete in one clock cycle. But if it's 64 clock cycles, it may take more than one clock cycle. And we have seen that multiplication is a much more complex operation than the integer addition. So multiplication operation takes several clock cycles, and the division operation, which we have not discussed, but it's more complex, so it can take even more number of cycles. This is for the integer operations. And we have seen that floating point operations, even the addition subtraction, is a complex operation. So typically floating point operations are all multi-cycle operations, right? So what it turns out is that except for the simple logical operations and maybe integer addition subtraction operations, all other arithmetic operations turn out to be multi-cycle operations, right? And in that case, the delta here will be greater than 0, right? And how much it will be greater than 0 depends on how many of this multiplication division for the integers are there in the given instruction sequence, and how many floating point operations are there in the given instruction sequence. And then we also see that the memory read and write operations are performed on this data memory. Again, it depends on whether the required memory variable operand is available in the data cache, that's the first level cache here, or it's available in the second or third levels of cache, or it may be there only in the main memory. Again, this may also lead to multi-cycle operations, right? So both in the case of the ALU and the memory read and write operations, right, it can result in multi-cycle operations. So this delta PO will be typically greater than 0. What is this delta PO we are talking about? On the average, how many more clock cycles are required to perform this operation per instruction? Okay. And when it comes to write back the result, where we write into the register file, and typically we use only the write port of the register file, and typically there will be only one destination register operand for the any instruction, like any arithmetic instruction or a load instruction, right? So in that case, the operation is simple, so we can complete within one clock cycle. So the delta W will be 0, right? So now, what will be the average time taken per the instruction now? It will be yeah, n plus 3 by n, right? So typically it requires n plus 3 clock cycles to execute these n instructions. So now we have to add this delta IF plus delta PO, right? And I mean, some entity related to this. I'm not saying that this is exactly this, right? So some entity related to this will be added to it. So that will tell you how many more clock cycles are required. Okay. Yeah, actually, if I define this delta IF and the delta PO as the additional number of clock cycles required on the average per instruction, right? Then we have to multiply this by n, right? And that actually, yeah, you can do that. So yeah, so this will be the additional number of clock cycles required totally, right? So this divided by n will give you the throughput in terms of the number of instructions per clock cycle. Okay, and for any real program, this will be larger than 0, right? So therefore, the number of clock cycles required will be greater than n. So your throughput will be less than 1. Okay. Yeah. Any questions about this? So this is actually related to only performing certain operations in the stages like instruction fetch and the perform operation, which take multi-cycle operations, right? So this assumption will not be valid whenever there are multi-cycle operations. And the name for this kind of cases or referred to as what is called the structural hazards that happen in the pipeline processor. It is mainly because the circuits that we have to perform the instruction fetch and the ALU operations or the memory operations in the perform operation, right, will not enable us to perform the operations in one clock cycle, right? So that's why these are called the structural hazards. And there's nothing much that one can do as far as the memory operations are concerned, unless you have larger cache memories and faster cache memories, right? It's not possible to reduce this delta IF and the delta PO related to the memory operations. And what has been done with respect to the ALU is that this ALU can be designed as a pipelined ALU. I'll briefly mention this, but we'll study it in the next course, right? So right now we are thinking of this ALU as a monolithic block where we pass on the operands, right? And then it will do the necessary processing and then produce the result, and we'll wait until the result is available before we can take the next pair of operands and then perform the operations in that. But typically, if you look at the circuits that were designed for the arithmetic operations, right? Within that arithmetic operation, there are what are called sub operations that you need to perform, and there can be overlapped sub operations within an arithmetic operation. I'll just give you a simple example. When you look at the integer multiplication operation, right? What is it we have in the integer multiplication operation typically? So if you look at the integer multiplier circuit, right, we have seen that there are two stages here. I mean, there are two parts here. One is the sum and reduction using carry save addition, right? And then the final addition of the last two summands, right? And the logic that's used to perform the sum and reduction is different from the logic that's used for the addition of the final summands, right? Let's say if I have two different multiplication operations to be carried out, let's say z equal to x multiplied by y and c equal to a multiplied by b, one after another, right? So if I start the operations for multiplication of x and y in the multiplier circuit, right, in the conventional method, right, I have to wait until this multiplication operation for x and y is completed before we start the multiplication operation for the a and b, right? But noting that there are two parts in this multiplier circuit, if I say that this is one stage of multiplier circuit, this is another stage of the multiplier circuit, first I complete the sum and reduction for the x and y, then I pass the results of that, basically where we have only final two summands to be added, then I'll pass it on to the next stage here, that is the addition of final summands. When the addition of final summands for the x and y operands are being carried out there, I can get started with the sum and reduction for the next pair of operands a and b. So again, we see that we are doing overlapped operations here, overlapped sub operations here, right? So we are talking about what is called the pipeline arithmetic and logic unit. So basically, this will also help us to reduce the time it takes to perform multiple arithmetic operations, right, when we use this pipeline ALU. So the principles are similar to the pipeline processor, but we are talking about pipelining within the arithmetic and logic unit. And typically, this can be done for several of the arithmetic operations that we have seen. It can be done for the integer multiplication operation. It can be done for the floating point arithmetic operations, right? So in most of the current day processors, you will see that this arithmetic and logic unit will be pipeline, okay? And it's also possible to perform the pipeline operations for the memory unit. I'm not going to discuss that now because that requires a lot more details to be brought in, okay? So it's also in principle possible to design the memory operations in a pipeline manner, okay? Maybe you'll study them in the next course, right? So typically what we are saying is that this perform operation stage, right, can be typically pipeline further, right? So by that, you are effectively reducing the number of multi-cycle operations. So if there are two stages in the perform operation, let's say PO1 and PO2, right? It will be 5 stages in the pipeline in the processor, and the delta PO1 and delta PO2 can be greater than 0, but they'll be much smaller than this delta P, right? So that's one of the ways to counter this what are called the structural hazards that happen because of the multi-cycle operations in the pipeline process. Yeah. Any questions about that? Again, I'm giving you only the basic principles. There are a lot of details that need to be looked into, right? And that will be done in the next level course. Okay. If there are no questions about that, let me go to the next assumption that we made here, that there are no dependencies among the instructions, and that may not be true in several cases, right? What do you mean by the dependency? When I have sequence of instructions, right, I1, I2, so on, In, here I'm assuming that I2 is not dependent on the result that's produced by I1, I3 is not dependent on the results produced by I2 or I1, and so on, right? That is, if I want to have 4 instructions in the pipeline, right, there should not be any dependency among the 4 instructions. And what is the dependency that we are talking about? Let us take a simple example. Suppose I want to perform the multiplication, the operations like this. A plus B plus C, right? So what is the sequence of instructions for this in the RISC processor? Right? Let's assume that these are already available in the registers, just to make the discussion simpler. And I want to put the result in the register R3, right? So if the values of A and B are available in the registers R0 and R1, I have to add R0 and R1, and I will use another register, let's say R4, to store the result of this, right? What is the next instruction that I need to carry out? To the sum of these A and B that are available in the registers R0 and R1, right, that is R4, right, I need to add R2, right, and then maybe I'll put the result in R3, then I may perform store operation, right? Store operation involves writing the contents of the register R3 into the memory location D, right? So what is it we see here now? If let's say this is the instruction 1 and this is the instruction 2 and this is the instruction 3, right? We see that the source operand for the instruction 2, that is R4, is the destination operand of the first instruction, right? So we see that this instruction 2 is dependent on the result that's being produced by the instruction 1. In the same way, we see that the source operand for the store instruction here is same as the destination operand of the instruction I2, right? So when can I perform this second addition operation? I can perform second addition operation only after the first instruction is completed and the result is available in the R4, right? So if you go back and then see the flow of the instructions in the pipeline, right? If this is my add R0, comma R1 and R4, when will the result be available in R4? Only here, after the end of the clock cycle, right? When do I look for this register R4 for the next instruction here? That is so for the second instruction, when I perform the operand fetch in this clock cycle, right, I look for the value in the register R4, but I don't have the valid value in the register R4 because the R4 is going to be produced. R4 is going to have the valid value, right, only after the instruction 1 is completed. All right. So I need to wait for this operation to take place until the previous instruction is completely executed. All right. Otherwise, I will get the wrong value in this register R4, right? Not the value that I am looking for here, right? And typically, these kind of dependencies will be there in several parts of the instruction, right? So in that case, what is it I need to do here? I have to delay this instruction decode operation for this instruction 2 by one more clock cycle, right? And then perform this instruction decode operation in the clock cycle 5, right? So until then, the clock cycle 3 and 4 will not be doing any operations in the I2, and therefore will not be able to do the operations for I3 and I4 in these stages. Okay, so basically this will result in more number of clock cycles being taken to complete the execution of each of these dependent instructions, right? And that will lead to again the increase in the total number of clock cycles that are required, right? So if I can say that the fraction of or the number of additional clock cycles required due to the dependencies, right, as delta dependency, right, and that will also contribute to this additional number of clock cycles, right? And typically, many programs that you write will have large number of dependencies among the typically the instructions which are close by to one another, right? And those cases will lead to this additional number of clock cycles being taken to complete the execution of those instructions. Okay. Again, there are some methods we bring in to reduce this number of clock cycles being additionally required, right? So that we reduce that delta dependency component. Okay. And if you just pay attention to the kind of translation of the high-level language statements into the machine-level instructions, right? You will quickly note that there are several such dependencies one can have, right, among the instructions for the given program. Okay, so this is a one more source for the additional number of clock cycles that are required, right? And these kind of operations that require additional number of clock cycles are what are referred to as the data hazards, because they happen because of the data dependency among the instructions. Okay, yeah. Any questions about that? Again, I'm not talking about solutions, right, to reduce this number of data hazards or the clock cycles that are additionally taken for these cases, right? I'm only telling you what is the problem, which can lead to a lesser throughput than the ideal throughput. Okay. Now let's look at the final assumption here, that there is no control dependency. What do you mean by control dependency? Typically, if you have the statements like if then statements, like what you have seen, a simple example. Right? How does this sequence of how does this statement get translated into this? Like again, let's assume that these are all in some registers, right? So typically we compare these A and B, which are all in the registers R0, R1, right? And then we see that if it is less than or equal to, let's see. I mean, I'm not sure what you written. Okay. If it is less than or equal to, we go to the else part. Otherwise, we perform the subtraction. And then put the result in the R3, right? Then this will be the else part. Or I mean, we'll have jump here. right? Then NDIF, right? We store. Okay. Okay, let's say this is out. Right? So what is it we have here? We have a conditional jump instruction here, and then we have an unconditional jump instruction here. Right? So let's say this is instruction 1, this is instruction 2, and so on. Right? Now what is happening? When this instruction 2 is being processed, when do I know whether this condition is going to be true or not? Only when I decode the instruction, when I look for this condition to be checked up, right? Then I look at the flags, states of flags associated with the ALU, right? And only after checking them, I'll be able to determine that whether the condition is true or not, whether this jump has to take place or not. By the time I do that, where is this going to be done? This is going to be done in the instruction decode stage, because only in the instruction decode stage, control unit is going to look at the instruction, then determine that it's a conditional branch instruction. It will check what is the condition to be checked, verified, right? And whether that condition is true or not. So all of that will happen in the instruction decode phase. By the time I process this and then decide whether the jump has to be taken or not, right? I already have the next instructions in the pipeline. Now, if the condition is that the jump has to take place, right, then I'm going to start the execution of the instructions at a different instruction than the next instruction, right? Let's say in this case, if this condition is true, right, where is the else part here? It is I4, right? And here I have the jump instruction to endif, which is I6. So it is not just the next instruction, it will be some later instruction. And for the if then else statements where this then part and the else part are all fairly big bodies, that is, large number of statements are there in the then part and large number of statements are there in the else part, right? The gap between the conditional branch instruction and where that part of the else part, the body of the else part is going to start, right? There will be a lot of gap, which means that I'm going to make a jump to an instruction which is much later than this current instruction. And in that case, by the time I make a decision whether the condition is going to be true or not, and whether the jump has to be taking place or not, already I will have a few instructions in the pipeline, and those instructions are not supposed to be executed because the jump is taking place, and these instructions need to be taken out of the pipeline. All right. And what are the processing we have done for those instructions which already entered the pipeline need to be discarded. So we basically effectively lose some number of clock cycles, right? And these kind of cases are referred to as what are known as the control hazards. So this is typically associated with all the jump instructions or the call instruction, right? And the I mean, when I say jump instructions, it can be unconditional jump instructions or the conditional jump instructions. Okay, and typically in any program there will be a number of such branch instructions and the function calls, and I think the estimate is that typically 15 to 20% of your instructions are all jump instructions and the function call instructions, right? And every time we come across this conditional jump instruction or a call instruction, right, we have to flush the pipeline, which means that there are some number of clock cycles that are lost. So again, if I indicate that by another factor called the delta control, right, then on the average, the number of clock cycles that we lost per instruction due to this control dependencies, right, if I denote that by delta control, right, again, that will be contributing to the additional number of clock cycles will be taken, right, to complete the execution of the instructions, right? So we see that there are several components that can lead to actual number of clock cycles being taken to complete the execution of instructions to be greater than this n+3, which means that my throughput is going to be less than 1, right? And how much it will be less than 1 depends on the values of these different deltas. Okay. Again, there are number of methods that are being used to reduce the effect of these hazards. Again, I'll just give the name here. Okay, but we'll not discuss that here. Is it possible to do a prediction of whether a particular condition is going to be true or not for a conditional branch instruction, right? Actually, if you remember, no, we mentioned about what is called the saturating binary counter, saturating up-down counter. Actually, the saturating up-down counter is used in the dynamic branch prediction, where we try to make a prediction associated with the particular conditional branch instruction based on that history of that instruction in the previous executions of that instruction. And that's where these saturating counters are going to be used. That will be part of the logic in the control unit. Okay, and this branch prediction is typically used to see if the prediction can be made correctly as in many cases as possible, so that we reduce the number of clock cycles that are lost due to these control hazards. Okay, so all these techniques are going to be discussed in detail in the next course, right? But here I just want you to get an idea that, or indication that, right, the ideal assumptions will not be holding good in the execution of the real programs, right? So typically one has to deal with these three conditions being not true, or these three assumptions being not true, right, due to these different types of hazards, and that can lead to the ideal throughput being less than one instruction per clock cycle. Okay, and how much it's less than one instruction per clock cycle will be dependent on how effective are the different methods that are used to deal with these different types of hazards. Okay, yeah, any questions about that? Okay, I'll briefly mention one more point, then we'll close the discussion on this. Right now we are talking about only one instruction being handled in any of these stages in the pipeline, right? That's what you've seen in the pipeline flow diagram. Typically, if you look at in any clock cycle, there's only one of these instructions which is present in a particular stage of the pipeline, right? And is it possible to have more than one instruction in the pipeline stage, right? Or the question can also be put, can I have several pipelines in the processor architecture, so that what is the reason why I want to go for the multiple pipelines which can be handling different instructions in parallel, right? Basically, now we can afford to have multiple instructions being processed in parallel, right? And the time taken to execute the sequence of instructions can be reduced significantly if I can afford to perform the operations required for multiple instructions in the parallel pipelines. I mean, just to put the things in a simple way, suppose I use two different pipelines. Each of these pipelines will have these stages, right? I have the sequence of instructions I1, I2, so on, right? Let's say all the odd numbered instructions will go here, and all the even numbered instructions will go here. Okay, I mean, this is actually a very simple thing. In reality, it's going to be completely different. Okay, so I1 will be sent through this pipeline, and I2 will be sent through the next pipeline, and both these pipelines are similar, right? And I can perform the operations for both the instructions in parallel in the two different pipelines, right? In the ideal conditions, what is the number of clock cycles required to complete the execution of these n instructions now? Yeah. So the number of odd numbered instructions is n by 2, and the number of even numbered instructions is going to be n by 2. So this will require n by 2 plus 3 clock cycles. This will require n by 2 plus 3 clock cycles. Again, this is under the ideal conditions. Right? But what is it we need in order to support this? I should be able to perform the instruction fetch for 2 instructions. I should be able to perform the instruction decode and register operand fetch for 2 different instructions, right? Then I need to perform the arithmetic and logic operations or the memory operations for 2 instructions simultaneously. Then I should be able to perform the write back operations for the 2 instructions simultaneously. Basically, this requires a lot more additional hardware, right, which is going to be duplicated, and then we need to provide the support for performing the operations for the 2 different instructions simultaneously. That's why these are called the parallel pipelines. Is there any problem to have 2 ALUs within the processor? Yeah. Instead of having only 1 ALU, can I have 2 ALUs? If I can afford to have more number of gates in the processor chip, right, I can have 2 ALUs. How does it help to have 2 ALUs? 1 ALU can be used to perform the operations for these odd numbered instructions, and another ALU can be used to perform the operations for the even numbered instructions, right? And I can perform the operations simultaneously for these 2 different instructions, right? But please remember that we are making lots of assumptions here that there are no dependencies among these instructions, and I can go ahead with the operations for the 2 different instructions simultaneously in the multiple ALUs, right? So typically what we are talking about is that there will be multiple pipelines which can be used to handle multiple operations, multiple instructions simultaneously. And in many of the current day processors, there will be not just 2 pipelines, there will be several pipelines. There can be 4 or even 5 pipelines, right? And they need not be similar pipelines, they can be different pipelines, okay? And they handle different sets of subsets of the instructions, right, in each of the pipelines, right? So these kind of processors where we use multiple parallel pipelines are what are called the superscalar processors, right? And the target of these superscalar processors will be k instructions per clock cycle, where the k is the number of parallel pipelines we have. So if I have 2 parallel pipelines, then I should be able to perform, in an ideal case, 2 instructions in every clock cycle. If k is 3, then it will be 3 instructions per clock cycle. But because of the assumptions being not valid, right, it can be slightly less than k, right? So what is we are now talking about? If I have a 1 gigahertz processor where the clock cycle is clock period is 1 nanoseconds. Earlier, we are talking about in pipeline processor, 1 instruction being completed effectively in 1 nanosecond. Here, we are talking about k instructions being completed in 1 nanosecond or in 1 clock cycle. Okay, so that's what many of the current day processors are capable of, right? So typically, they have the potential to achieve a throughput of more than 1 instruction per clock cycle. It will be typically anywhere around 2.5 to 3, depending on the value of this k, right? And depending on the dependencies among the instructions and so on. Okay, so I just want to give a hint there and then close the discussion on this mechanism that's required to facilitate the overlapped operations as well as the parallel operations among the instructions. All of this is by exploiting what is called the instruction level parallelism. That is, we are trying to exploit that's parallelism that's present at the instruction level and then provide the support in the processor architecture, right, to exploit this instructional parallelism and then see how the throughput can be made higher for this. Okay, maybe I'll stop the discussion on this now. Are there any questions? Okay, maybe I'll stop here. We'll continue the discussion on next class on Monday. Okay, bye then.